Hello there, Mr. Sutton bringing you this BC Calculus 8.6 Extra Practice number 4 solutions on polar functions advanced area. Here we go. On this no calculator problem, we're told that R is the region in the first and second quadrants between the graphs of f of theta and g of theta, and they didn't really tell us which one was which, so we're going to have to kind of figure that out without a calculator. We want to know which integral gives the area of R. Okay, so it looks like I'm going from essentially 0 to pi for my angles, but I need to know again which function is which. My general strategy here, I'm going to be using the polar area formula, which is integral from a to b of 1/2 r squared d theta. So my limits of integration definitely going to be from 0 to pi, because I'm involving angles here for polar area. So already I can eliminate choice A. That's just thinking about things from left to right. That would be like x integration, which we're not using here. So we're using either B, C, or D for the answer choice. But now my general strategy is I've got two different areas involved. I've got an area under this outer curve, and I also have the area under this inner curve. I want to basically do outer area minus inner area. So I'm going to have two integrals, and at some point I'm going to have to mash those up into one big integral. But now I need to figure out which curve is the outer curve and take that area. So to do this, let me start by just taking the f function, and I'm going to plug in the value 6, or actually the angle 0, just to see what we get back. We'll probably get a 6 back. So if I plug 0 into the f function, I end up with, let's see here, that's 3 plus 3 cosine of 0. Cosine of 0 is 1. 1 times 3 is 3. 3 plus 3 is 6. Big surprise there. Okay, but now let me do f of pi to see what value I get back for the radius for if I plug in pi as an angle. So cosine of pi is -1. So that's -3 that I'm adding to +3. That gives me back a value of 0. So we have a radius of 0 when I plug in pi. So that means that must be... this inner function must be f then. And then just to verify, if I plug 0 into the g function, so that's going to be 4 plus 2 cosine of 0. That's 4 plus 2, which is 6. And if I plug pi into the g function, I'm going to get basically 4 minus 2, which is 2. So that's saying that at pi radians, I have a radius of 2, which... This is what's going on. If you ended up at -2 for the x value, you were going 2 in the pi direction right here. So that tells us g is the outer function. So for my area then, I need to take the area under g and subtract the area under f. So I'm going to write the integral then. Area is going to be 1/2 integral from 0 to pi of, and now I need to do g, so 1/2 g of theta squared d theta, and I had the 1/2 outside, so that's that outer area. Now I have to subtract the inner area, so I'm going to subtract 1/2 times the interval from 0 to pi of f of theta squared. That's the area under f, and that's none of the answer choices, so I'm going to have to find a way to combine these. Since these both have a 1/2, I can factor that out and write 1/2 integral from 0 to pi. And then I'm just going to have to combine the stuff inside. So g of theta squared minus f of theta squared, d theta. So taking a look at the answer choices, that's going to be answer choice D. So we have to be very careful here because each of these functions is being squared individually before the subtraction is happening. You can't subtract them and then square like they were doing in choice C. It doesn't work that way. For this calculator-based problem, we have a figure showing the graphs of r equals 3, which is the big circle here with the radius of 3, and r equals 4 sine of theta. That's this smaller circle up here. We want the area inside 4 sine of theta and outside r equals 3. Okay, so basically, if we're inside the smaller circle and outside the bigger one, we're in this little crescent moon-shaped region up here at the very top. So we want that area. So my general strategy, I need to basically find the area of this smaller circle from this angle to this angle, and then subtract the area of the bigger circle from this angle to this angle. Just to be on the super safe side, though, I'm going to find just the first quadrant area in here and multiply it by 2. So that way I only have to find one angle of intersection, and my other angle is just going to be pi over 2. All right, well, I need to at least find this angle of intersection, so I need to figure out where 4 sine of theta and 3 intersect, so I'll do that on the calculator. Since I'm basically just trying to solve the equation 4 sine of theta equals 3 for theta, I'm not going to bother using polar mode or anything fancy like that. I'm just going to graph each side of this equation as a y equals and just see the intersection point. And now let me see here. This is going to happen somewhere between 0 and pi over 2. So I'll make that my window. So window 0 for x min and pi over 2 for my x max. And zoom fit. Let's see where these things are crossing. Zoom 0. So there's the left half of my equation, 4 sine of theta. And there's 3. So that intersection point, we do second trace, option 5 for intersect. Enter, enter, enter. Gives us an intersection point of 0.8481. And I'm going to refer to that as the value p from here on out, just so I don't have to keep writing it over and over again. And let me go on my calculator, and that's a super important value right there. So let me quit out of my graph, and I'm going to store that as alpha p. And you can choose whatever letter you want. I'm just using p. All right. So now that I have that intersection point, it's time for me to write out my area. So for my area, again, I'm going to be finding the area in this first quadrant sliver, this first half of this crescent moon, and I'm going to be doubling that. So my area is going to be 2 times something. All right, now for the something. So I basically got the difference of 2 different areas. I have the area under the small circle here from angle P to pi over 2, and I have to subtract that. From that, I have to subtract the area under the bigger circle from P to pi over 2. Both of those area formulas involve a 1/2. The general formula is 1/2 is going to be the integral from a to b of 1/2 r squared d theta. So since I'm going to have a 1/2 integral minus another 1/2 integral, I'm going to factor a 1/2 out of both of those. And in a big parentheses, I'm just going to have integrals with r squareds in them. So that's what I'm doing at this point. So I need my my outer function r squared. I need this 4 sine of theta squared integral. So that's going to be, again, from the angle P to pi over 2 of 4 sine of theta squared d theta. And I'm going to subtract the integral from P to pi over 2 of, and now I have to have that circle, so 3 squared d theta. All of this is going to basically, again, take just this little area in here and then multiply it by 2 to get that whole crescent moon area. And the rest of this happens on the calculator. Now, this looks like it's going to be a huge pain to enter in the calculator, but if we're a little bit clever about this and careful, then we can, kind of shortcut some of all this writing in. So for example, 2 times 1/2, well, we know that that's just 1. Those are going to cancel. So I don't really need to write that in my calculator at all. And now we just have these integrals. Now you might notice that both of these integrals have the same limits of integration. So we can actually combine this into one big integral using our definite integral rules. So I'm going to just have one integral, so math 9, from point P, so alpha P, to pi over 2. So let me do pi divided by 2. Okay, there we go. And inside here, I'm basically going to have this 4 sine of theta squared minus 3 squared. Well, now I can save a little bit more time here as well, because you might remember I entered 4 sine of theta as my y1. So I'm going to do alpha trace y1 and just square that. And for what it's worth, I actually entered 3 as my y2, but I don't think I need to do that much overkill. Let me just do minus 3 squared. But I could do minus y2 squared. And then let me just do dx, press enter, and that all comes out to 3.246, which gives me answer choice D. For this problem, we have the graph of the polar curve r equals theta, which, just a little trivia, that's called the spiral of Archimedes. And they're showing this on the interval from 0 to 3 pi. So we want the area of the shaded region. So this is kind of an interesting problem because very often the interval is from 0 to 2 pi, but here we're going to 3 pi. That means we're actually going multiple times around the unit circle. So here is 0, here is what we get at pi. Coming back around here, this is 2 pi for the angle, and then back around another 180 degrees, we come to 3 pi. So to get this area in between, just the general strategy here, I want to take the area of the circle between 2 pi and 3 pi, and I said the circle, I should say the curve, because it is a spiral here. So I want the area between 2 pi and 3 pi, and I want to subtract the area between just 0 and pi, this little unshaded area in here. So my area then, I'm going to have, my general area formula is basically 1/2 times the integral from a to b of r squared d theta. So I'm going to have 1/2 times the integral from 2 pi to 3 pi of, well, r squared d theta. That's basically theta squared in this case, d theta. And now from that, I'm going to subtract the area in here. So that's going to be 1/2 times the integral from 0 to just pi of really the same curve, but it's just a different interval of the curve. All right, so this is a no calculator problem, and we're going to have to simplify our answer, it looks like. So let me start by taking some antiderivatives. I've got, this bumps up to a 3, just using my reverse power rule. This bumps up to a 3, dividing by that, I have 1/3. So I've got a 1/2 times evaluation box 1/3 of theta to the third power, evaluated from 2 pi to 3 pi. And then I essentially have the same exact thing, but evaluated from 0 to pi, because everything else is the same in there. And that's what I'm subtracting. So when I evaluate this, because I want to save a little bit of time here, I can take a small shortcut. I can't put these in the same evaluation box because the limits of integration are different. However, you'll notice that these both are being multiplied by a 1/2, and that inside they're both being multiplied by a 1/3. Well, I could take the 1/3 out to make each of these a 1/6, and then I could just take that 1/6 out to have a 1/6 times just a whole bunch of stuff. So I have 1/6 times basically theta cubed with 3 pi plugged in minus this with 2 pi plugged in. So this would be a 3 pi quantity cubed minus 2 pi quantity cubed. So this bracket here takes care of this evaluation box. And then I'm going to subtract the results of this evaluation box, which after I take out that 1/6 is going to be just pi cubed minus 0 cubed. Got to simplify this. So this is going to be 27 pi cubed minus, this will be 8 pi cubed. And this is all inside of big parentheses with a 1/6 outside. And over here, I've got minus just pi cubed, and then that 0 is just gone. So this is 27 pi cubed minus basically 9 pi cubed, which is 18 pi cubed. And 1/6 times 18 pi cubed is going to be 3 pi cubed. So that ends up being choice B. On this problem, I have a graph of the polar curves r equals 2 plus cosine of theta and r equals 2 minus 2 cosine of theta. We want to know which of these gives an expression for the area of the region inside both curves. So this little kind of sort of heart-shaped area in here, but it's not really a true heart shape, but whatever you want to call it, that area. So one thing that would be very helpful in this problem is to know which curve is which, because they certainly didn't label them. Thanks. But that's okay. We'll figure it out without a calculator. So to figure out which is which, I'm just going to plug in the angle 0. So one of these curves, if you plug in the angle 0, one of these curves is at the pole, so it would give you back an r value of 0, and the other curve would give you back an r value of something else, not 0, whatever this number over here is. So let me try plugging 0 into this first curve, 2 plus cosine of theta. Cosine of 0 is just going to be 1, so this would be 2 plus 1, which would give me something that's not 0. So it might be this 3 over here. Maybe this is 3. Now let me try plugging 0 into this other function. Now we said cosine of 0 is 1, so this would be minus 2 times 1, or just simply minus 2. 2 minus 2 is 0. So this curve over here has got to be the one that's hitting the pole at the angle 0. So this rightmost curve, I'm going to call this 2 plus cosine of theta, so now I know what it is. And this other one then is 2 minus 2 cosine of theta. All right, now that I've got straight which one is which, I need to find the area that they share here. So there's a lot of different ways you could go about finding this area, but you have to kind of look at the answer choices to see what they're looking for. I mean, my initial thought would be just find the area of all this stuff between 0 and pi and then double it, but that doesn't really look to seem what they did down here. There's no like 0 to pi sort of thing going on. That's okay though. And we can't go from 0 to 2 pi because if you just think of the area as adding up all the radius slices, all the distances from the origin to the curve, well, that distance in this bounded area here is occupied by this one curve on the left, the 2 minus 2 cosine of theta, as you go from 0 to pi over 2, but then you're hitting this other curve between pi over 2 to 3 pi. And then you're going back to hitting that first curve between 3 pi, or I guess you could call that negative pi over 2, and 0. So this is an issue. You can't use a single integral from 0 to 2 pi to get this area. You have to split it up. So already this is indicating that probably answer A is no good. We're going to have to do one of these other ones with multiple integrals. Okay, so our general formula for the area, that's going to be 1/2 times the integral from a to b of r squared d theta. So I'm going to just take this first area here. So to get this area, I'm just using the r minus 2 cosine of theta curve, or r equals 2 minus 2 cosine of theta curve. And I'm going to use that from, I guess I'd have to go from negative pi over 2 to positive pi over 2 to get this area in here. So I'm going to do 1/2 integral negative pi over 2 to pi over 2 of 2 minus 2 cosine of theta, the whole thing squared, d theta. There we go. So that gives us these two little humps here to the right of the y-axis. Now I have to get all this stuff to the left of the y-axis. This little, it's almost kind of semicircular shaped. Now those limits of integration, we're going from pi over 2 to 3 pi over 2. So I've got 1/2 of an integral with those limits. And this time I'm using this rightmost function here, 2 plus cosine of theta, because we're hitting that curve now with these little radius slices. So I'll put this thing in there and square it, put a d theta next to it. And thankfully, I don't actually have to evaluate this. I just have to match it with one of my answer choices. So taking a close look here, doesn't look like it's going to be choice B. We already eliminated A. Choice C, let's see here. I've got 1/2 integral negative pi over 2 to pi over 2. That looks good. And then we're adding this stuff. So I think this matches answer choice C. Let me look at D because these look kind of similar. What's the difference between C and D? Well, in D, these things are not squared. They forgot to square their R value. So that means we've got to go with choice C. On this no calculator question, we're given a figure showing the graph of the polar curves R equals theta, which I happen to know is the spiral of Archimedes. It's this one that starts at the origin and comes out like this. And this other one, 2 theta plus 1, which must be this kind of wider, more spread out version of the spiral of Archimedes. And this is on the interval from 0 to 2 pi. So we want the area of the region bounded by these two polar curves over that interval. So we're looking for the area of this space in between the two curves. My general strategy is I want to find the area inside the curve of 2 theta plus 1, and I want to subtract the area that's inside the curve r equals theta. And if I subtract this smaller area from this larger area, that's going to give me this area in between. All right, so area in general, that's going to be 1/2 times the integral from a to b of r squared d theta. So I'm doing the outer curve, so I need to do 1/2, and now I need the integral from 0 to 2 pi. We want this whole interval here. And that's going to be 2 theta plus 1 quantity squared d theta inside, r squared d theta. And now we have to subtract the area inside the spiral of Archimedes. So minus 1/2 times the integral from 0 to 2 pi of just pi squared d theta, or pi squared theta squared d theta, mixing up my Greek letters. All right, so now we've got, let's see here. We have to use fundamental theorem essentially, and take antiderivatives and plug in limits of integration because we can't use a calculator for this. Before I do all that, though, I'm going to try to get this all inside one big integral. I think that would help me out. I have the same limits of integration, so that's a good step in the right direction. I also have this 1/2 in both of these. So it turns out I can combine this into just one big integral. I'm going to have 1/2 times the integral from 0 to 2 pi of, and now I'm just going to expand this and throw in this, this minus theta squared here. So expanding this squared parentheses, this is going to be 4 theta squared, and now I have to multiply these and double it for the middle. So that's going to be plus 4 theta, and then we have a 1 squared, so just 1. And now I have to subtract the stuff that was inside this integral, so minus theta squared, d theta for all of that. And then if I just clean that up a little bit, my final definite integral, I'm going to have 1/2 integral 0 to 2 pi of 3 theta squared. I keep wanting to say pi. 3 theta squared plus 4 theta plus 1. Great. So now at this point, it's time for some antiderivatives. We're going to use the reverse power rule. So this one is going to bump up to a power of 3. Dividing by that, I just have theta cubed, and I still have a 1/2 outside all of this. Next, this bumps up to theta squared. Dividing by 2, we've got 2 theta squared. And then this plus 1 turns into a plus theta because we're differentiating with respect to theta. All of this evaluated from 0 to 2 pi. So I've got 1/2 times all this stuff with 2 pi plugged in minus all this stuff with 0 plugged in. So going through, I've got a 1/2 times, and in here, let's see, this is going to be 8 pi cubed plus, well, let's see, you have to square it first. So initially it's 4 pi squared, but now it becomes 8 pi squared. This is just still 2 pi, and everything over here gets zeroed out, so I can close that parentheses. Nothing in here can be combined. These all have different exponents on the pi, but I can multiply this 1/2 because I don't have a 1/2 in any of the answer choices. So distributing that, we've got 4 pi cubed plus 4 pi squared plus pi, which ends up giving me answer choice D. For this calculator-based free response problem, we have this region S bounded by the polar curve r of theta, which is all this craziness over here, on the interval from 0 to radical pi. Great. We want to find the area of S as the first task on this. So in general, my area for a polar curve is going to be A equals integral from A to B of 1/2 r squared d theta. So in this case, I'm going to have the integral from, they gave us the curve's interval here. It's from 0 to the square root of pi of, and now we're going to do 1/2 times, well, r squared d theta. Here's your r. Here's your polar curve. There's just one thing here. There's no tricks or anything else like that. We just have to take half of this thing that's being squared. So we do 1/2 r of theta squared d theta, and just got to plug it in the calculator. To make this part of the problem, and maybe the rest of it a little less painful, I've entered my r of theta as my y1 in my y equals of the calculator, and I have to do everything in terms of x because that's the variable that the function mode with y equals uses, but it is what it is. So quitting out of there now, I'm doing the integral, so math 9, of, let's see, going from 0 to the square root of pi, so square root of pi. It's fun to enter. And then inside here, we have 1/2, so fancy fraction, 1/2. And so now we save a little bit of time because I entered this whole thing as my y1. So I'm just going to do alpha trace y1. Don't forget to square that. Put a little dx over here. Press enter. Hope for the best. And we end up with an area of 3.534. For this part of the problem, they want the average distance from the origin to a point on this polar curve that they gave us over the interval from 0 to radical pi. Now, the key here is recognizing that the function r of theta actually gives you the distance from the origin to that point. So, in order to find the average distance, we just need to set up an average value kind of integral involving r of theta. So, using my average value setup, I just have 1 over the interval length, so 1 over radical pi minus 0, times the integral from 0 to radical pi of the thing we're trying to average, which is just this r of theta. So we'll put r of theta d theta. And they already spelled out what it was, so I don't have to rewrite it. So now I can just take this integral and call it a day on this one. So here's what this looks like on the calculator. I'm just doing 1 over radical pi. I'm not going to bother writing minus 0. I've got my integral, 0 to radical pi. I stored r of theta as y1 in my calculator back in part A. Put a little x next to the d, press enter. My average value is 1.580 if I round off to 3 decimals. For this problem, they're telling us there's a line through the origin with a positive slope m that divides S into 2 regions of equal areas. They want us to write but not solve an equation with one or more integrals whose solution gives the value of m. So basically, we have this line m, or with a slope of m anyway, cutting this into 2 equal areas. So the equation that I would set up would probably have these 2 different areas expressed, and there's going to be an m in there somehow. Now, how does the slope m figure into all of this? Well, if you're writing equations or if you're writing integrals that give you areas, you need limits of integration. We took the area of this whole, we found the area of this whole region S in part A, and it was the integral from 0 to radical pi. So we already did that, but we can't do that anymore on this problem because we have this m chopping this thing into 2 halves. So I'm going to have 2 separate integrals. One is going from 0 to, well, whatever the angle is that line is going through. And then one is going to go from that mystery angle from that all the way to radical pi. So I have to figure out kind of my angle that is separating one integral from the other. Well, the good news is if you have a slope of m, the angle that gives you that slope, we can find that angle by just using arctan. So the angle formed by slope m is just going to be the arctan of m. Remember, tan takes an angle and gives you back the slope. Arctan takes the slope and gives you back the angle. So I'm going to have one area for a part of S. That's going to be, so 1/2 integral from 0 to m, or arctan of m, I should say, because that's the actual angle, arctan of m. We're going to have 1/2 times, we said it was r squared d theta, so 1/2 just r of theta squared d theta. So this gives us the area from 0 to whatever that line was chopping this in half. I'm going to say that since those areas are equal, this has to equal the integral from arctan of m to radical pi of basically the same area formula, 1/2 r of theta squared d theta. And now I have an equation with one or more integrals that has an m in it that I could solve to find the value of m. For the final boss battle on this one, they're saying for positive k values, let a of k be the area of the portion of region S that is also inside the circle r equals k cosine of theta. So there's this other circle being graphed on here that overlaps S for part of it, and a of k is just the region inside there. But k can change. In fact, they want to know the limit as k approaches infinity of this area. All right, well, I think it would help if I had a kind of a visual of where these things are overlapping. So let me graph all this out, and I'm going to have to use the polar mode on my calculator. So on my calculator, let me go to mode, and I'll go down here and change from func mode to pol mode, polar mode. And now if we go to y equals, it's no longer y equals. Now it's r equals. Let me graph the original here. So we've got 3 and then radical theta. Now to get theta, I have to do the x button. And let me arrow out of that radical. We do sine of theta squared, parentheses, good deal. And let me just graph this out to make sure it's correct. So let me go to window and let me make sure I have the right interval. We just want to graph this from 0 to radical pi. It's a good idea to take their advice on this integral or on this interval. You don't really want to stray outside of that because you're going to get a whole bunch of stuff that doesn't make sense that you didn't really want anyway. All right, and let me just do zoom 0, zoom fit to see what this looks like. Okay, that looks like it could be the same curve, more or less. All right, so let me go back into y equals, r equals, and now I'm going to graph this circle. Now, it's not going to look like a circle when I graph it because I'm only going to be graphing it on the same interval as the r of theta function from 0 to radical pi, so it's going to be a piece of the circle, probably in the same quadrants that S is in. So let me do Well, let's see here. K. What is K? I don't know what K is. But let me start with some kind of value of K. Let me let K equal 1 in the beginning here, and then we can start changing it and see what happens. So I'll write 1 cosine of theta just because I have to start somewhere. I just want to get kind of a visual of what this looks like. And now if I graph this out, there is the piece of the circle that I graph on the interval from 0 to radical pi. So there's this tiny kind of sliver of overlapping region. Okay, let's go back to the r equals, and now let's change that to, no, we don't be too ambitious. Let's make it a 2. 2 cosine, so k is 2. Go back to my graph. There's the original, and that region has gotten a little bit bigger. Okay, let's do a k value of, let's double that. Make it 4. So going back, there's the original. There's my circle. We're getting more of that area. All right, this could take all day here. Let me double it again to 8 and graph. Still more. All right, we're going for broke here. Let me make this, let me see here. Let me insert, let me make this 20. 20, that seems like a good number. And let me insert a 0 in there. All right, graph this out. So we keep getting more and more, it seems, overlapping area. Now let's just contemplate what would happen as k gets really big. Let's just do one more here, and I don't feel like inserting more numbers. Let's make this 99. I mean, that's got to have some effect, right? So k value of 99, here's what this looks like. We're getting more and more of that S region overlapped in there. So what's going on as your k value increases, your circle is overlapping pretty much the entire S region in the first quadrant. Now, the circle's never going to stray outside of the first quadrant. It's always staying in that first quadrant. But as k gets bigger, your circle gets bigger, overlaps more of S in the first quadrant. So then the limit, as k approaches infinity, of this overlapping area is just going to end up being the same as the area of S itself in the first quadrant. So let's go ahead now and write out what that limit should actually be. So limit, as k approaches infinity, of a of k, I'm going to say that's equivalent to basically area of S in the first quadrant. So that's an integral from 0 to pi over 2 now, not radical pi, just pi over 2, first quadrant, of, now we have 1/2 r squared d theta, so 1/2 r of theta squared d theta. And now I just have to plug that in the calculator. Now, it's up to you whether you want to go back into func mode or stay in polar mode to do this integral. You can actually stay in polar mode. It won't really matter. So let me do math 9 for my integral. That's going to be from, we said 0 to pi over 2, just the first quadrant. So pi divided by 2. There we go. And inside we're doing 1/2. So fancy fraction time. 1/2. And now I stored this r of theta as r1. So let me do alpha trace. And now it's r1 that it writes instead of y1, but it's the same function really. Don't forget to square that. And now if you press X, it's a d theta, so it actually looks like it looks on the paper, which has got to be kind of satisfying. Press enter, and that comes out to 3.324.